Hello, everyone, and welcome to Leilani Hedrina Gilpin's PhD thesis defense. Ms. Gilpin is about to summarize for us the work that she has been doing for her doctoral thesis. We thank you for coming. Ms. Gilpin arrived in our group in 2016. She arrived from California, where she worked at Park. My friend and former student, Johan de Cleer, is there, and also at Stanford University. Since then, she's been working hard on understanding how to make complex machines work better by giving them the ability to explain their decisions and their actions, specifically by giving the subsystems of a mechanism a way to symbolically explain their behavior to neighboring subsystems. And she makes that makes it possible for disagreements to be manifest and perhaps be moderated or corrected by supervisory subsystems. Over the same time, Ms. Gilpin has been deeply involved in the MIT community. She was the Visit Day and Orientation Vice President of the EECS Graduate Student Association for 2016. She is the Academics and Diversity Vice President for EECS Graduate Student Association. And she's also been a graduate resident tutor for Burton Connor, an undergraduate dormitory. Ms. Gilpin is a fine teacher. She did a great job of teaching my teaching assistant for my class, Large-Scale Symbolic Systems, about 2 years ago, I think. She also created a class on artificial intelligence and global risks that was given in the independent activities period of 2018. But I think I'm taking too much time. It's time to hear from Leilani. Just a few rules. Please mute yourself, okay? And use Zoom to raise your hand if you want to ask a question. Please stay muted until you are acknowledged by Leilani or Lalana. Then unmute and ask your question. Please mute after you've asked to avoid bad echoes. Also, please say your name before asking your question. One other thing. Each person in the room who has a doctorate degree in any subject, including things like English literature, please send me your name and affiliation so I can put that in the report. Lalana will put a Google Doc address in the chat for you to add that to. I think that's what's needed right now. So, okay, Leilani, it's your turn.
Great. So hi, everyone. Thank you for that really nice introduction. I'm really excited to be here to talk about what I've been working on for the last several years and something I call anomaly detection through explanations. In particular, I'll be talking about two novel ways to think about explanations. One is explanations for people, so explanations for external users or investigators, but also the novel use of explanations for the machine, the way that a machine can use the explanation of its underlying parts to reconcile errors and failures. In particular, for the agenda today, I'm going to start by motivating the problem that systems are imperfect. And I'll talk about the solutions that I've come up with, in particular, local sanity checks for local subsystems, and how I tied that into a system architecture to do better failure detection. And that's all leading towards my vision to have articulate machines by design, designs that are machines that can communicate coherently and to their underlying parts. In particular, the question that I'm asking through my thesis research is how can I develop self-explaining architectures that are more adaptable, more robust, and interpretable. And this is an important thing to think about, especially in the context that complex systems fail in very complex ways. Just a couple days ago, Nissan expanded their recall because hoods could open unexpectedly. This is a small mechanical error that could have huge failures if this occurred, in the middle of the freeway or even in residential driving where this is an unexpected behavior. Now, these failures are only illuminated when we consider autonomous agents that are now taking control of decisions that were previously entrusted to humans. In fact, autonomous agents fail in ways a human never would. In China, there was an AI that mistook a bus side ad for a famous CEO and charged her with jaywalking. It's something that looked like this, and this is a case where a human would never mistake that for someone jaywalking. These are situations that have immense circumstances. And finally, this occurs in complex systems that are outside of the autonomous vehicle realm, although the focus of my dissertation research has been on the application of self-driving. In our own computers, we have things where if you upgrade or downgrade an operating system, you can get version skew. So for example, here, I was trying to access user bin where I was able to access it just a couple of days ago. And now once I upgraded my operating system, that operation is no longer permitted. This happens happens all the time when you upgrade or downgrade your operating system on your computer or your smartphone or in many other smart devices that we have. And we also have failures that occur when the explanations that are given to us are just imprecise. This is telling me to enter the password for my email account, for my CSAIL email account, lgilpin@csail.mit.edu, but actually this error message is incorrect and imprecise. So actually this has nothing to do with my password whatsoever, but it's an imprecise explanation. I would want it to come back and say, actually the certificate is missing, and that's the root cause of this failure. Now, we do have some existing software solutions that can deal with these problems, especially the ones on our own computers. In fact, we have verification and unit testing and other types of diagnostic systems that can look at software systems and give strong guarantees and provable properties about the underlying processes. But the problem is this doesn't scale well to the types of open environments that occur in things like self-driving. In fact, it is impossible to test all failure modes in these types of open environments. And we see this in the self-driving solutions that exist today. In fact, autonomous vehicle solutions are at two different extremes. If you look at caution and comfort, then you can see that there are very cautious but not comfortable self-driving cars like the herky-jerky ride in General Motors' ultra-cautious self-driving car, where it would constantly start and stop for anything that it saw in its way, whether that was a translucent plastic bag or a large moving object like a person crossing the street. At the other side of the spectrum, you have self-driving cars that are very comfortable, but not cautious at all. In fact, there was a safety lapse, which led to Uber's fatal self-driving car crash, and that's actually been documented in legal records. And so what we really need is the type of reasoning that humans can do. In fact, we need better common sense and better reasoning, because this is also important for complex systems that include people. In fact, we make mistakes, and this is usually due to a lack of communication caused by a misalignment of expectation. In fact, in my own living community, we have an expectation that everybody shares food in the refrigerator, but when one of the food items is finished, sometimes that isn't communicated well to the rest of the community. And in fact, that can cause a big error. So when someone is expecting that their food is still there in the morning, then this expectation is misaligned. And so what we would really want is better communication. And in fact, if you look at human organizations, they have the built-in structures to deal with these types of flaws and failures. So my big question has been, how do we take these structures and then apply that to a complex system? And in fact, that's exactly what I've been working on in my PhD research, is to create architectures that are inspired by human organization. And they incorporate two major contributions: better communication amongst the parts of a complex system, as well as individual sanity checks around local subsystems. And so if we think about the way that this works in a human organization, largely you have a human organization that is organized into a hierarchy of overlapping committees. For example, you might have one committee that is made up of people doing software development, and they're all speaking that technical language, and another committee that's working on quality assurance and unit tests. Yet these committees are also overlapping. There are many people that may work on software development as well as quality assurance, and they bridge the gap between the communication between the two committees. And then there's also constant interaction and communication amongst the committee. They're constantly talking about what they're doing and justifying their action. This is the idea that inspires the local sanity checks that I've built for the different subsystems and parts of a complex system. And finally, if a failure occurs, then we can create a story or an explanation by combining the members' observations. And that's exactly what I've done with an explanation synthesizer that examines the underlying explanations of the underlying subsystems, and then synthesizes them and figures out if there are inconsistencies. And in the case of inconsistencies, it figures out which one to discount. Now, how did I actually do that? I basically applied this architecture to a self-driving car. So the local sanity checks can deal with issues like the trollable self-driving car, where self-driving cars can't reason about new examples. So this local sanity check is able to justify new examples and even reason about things it hasn't seen before. For example, if the self-driving car hasn't seen a person walking with a bicycle, even if it can't identify what it is, it knows that it's a big moving object, and there are certain reasons that we would want to avoid that. Now, on the other side, the synthesizer is able to reconcile conflicting reasons. And this is what happened in the Uber self-driving car accident, which will be a long running example throughout my thesis work. And so this is able to deal with conflicting reasons. In fact, what happened in the Uber self-driving car accident is that there were two systems. There was a LiDAR system, which is perceiving the world and producing large point clouds of data, and a vision system that was trying to give high-level concepts to what it perceived. And unfortunately, the system was only looking at the modality of vision during that time. And so if we actually visit what happened in this self-driving car accident, you will see a person coming out of the shadows. And unfortunately, the car didn't detect the person with enough time to stop. And again, the reason why is because the architecture that was on the self-driving car was only looking at the vision modality. It wasn't looking at the LiDAR and the vision together. In fact, if it did, it would have found that they conflicted and maybe they should reason about this system. So in fact, I specified an architecture that can deal with these uncertain judgments. In fact, I created an architecture called anomaly detection through explanation, which facilitates better communication amongst the underlying parts. And along with this synthesizer, if you put in the log of the accident after the fact, you get the output explanation that the best option is to veer and slow down. The vehicle is traveling too fast to suddenly stop. The vision system is inconsistent, but the LiDAR system has provided a reasonable and strong claim to avoid the object moving across the street. And you can see here highlighted in the specific colors where those explanations actually come from. They came from the underlying parts. And this is the architecture that I'm going to be talking about today. But first, to start, I'm going to talk about the individual sanity checks that I've created for individual subsystems, and then we'll move towards the system architecture in the final part of the technical portion. Now, my thesis relies on the fact that complex systems can fail in two ways. So the first type of failure is a module failure. So the failure could be local to a specific subsystem. The second type of failure could be due to a failed interaction or a failed cooperation amongst subsystems. Now I'm going to talk about both of these, but for the first part of the talk, I'm going to talk about the local failures. And in particular, I built two types of sanity checks for the subsystems of a self-driving car. I built one for the camera system and one for the LiDAR unit, which I'll briefly touch on. But for this portion of the talk, I'm going to talk about what I did to make sanity checks for the camera section of the car. In fact, if we look at how a self-driving car deals with camera data, a neural network usually labels the camera data. So what happens is the cameras output an image, something like this. This is an actual image from New Scenes. That's a self-driving car data set, which I'll revisit later in this talk. And it's passed through some sort of deep neural network. This is the Inception network from Google that does a very good job at labeling some of these images. And what's output here is a label. In this case, it says that it is a pedestrian. Now, neural networks do a really great job at labeling the different parts of images, but the problem is that when they fail in ways a human never would. So one example are adversarial examples where you can add a little bit of noise to an image. So something like this pig image with a little bit of noise that we can't see. Suddenly the neural network now classifies this as an airliner. In fact, it doesn't take into account any of the context of this image. It just classifies it as something completely different. But now imagine if this same type of technology is being put on self-driving cars. Well, they can also be tricked in these sorts of ways. So for example, with a couple pieces of tape, and this was actually shown in this paper, you can fool a deep neural network into thinking that this stop sign is actually a 45-mile-per-hour sign. And you can imagine these types of tricks are just endless. You can't represent all of these tricks in training data. And so the point I'm trying to get across is that these types of mistakes in self-driving or other mission critical, safety critical applications, they have consequences. And so what we really want to do is make sure that these systems work a little bit better. And to do that, I created a monitor. So I created a reasonableness monitor that would monitor opaque subsystems for reasonable behavior. And so what I do is I take this pipeline process and I treat the intermediate deep neural network as an opaque mechanism. And then I look specifically at the output to see if the output is reasonable given the context and other information that we can gather about what's being seen. And I do that with a common sense knowledge base, along with a flexible representation of what's being done in the car and how to represent the additional common sense that I'm using. And I check that against a plethora of different rules that can identify unreasonable behavior. And then finally, I use that to justify whether the output is unreasonable or reasonable. Again, this entire structure is leading towards one, a judgment of reasonableness, and two, a justification of reasonableness. And so the way that I actually created that is in the reasonableness monitor architecture, and you can see where the different parts here are. I'm going to walk through the individual technical contributions of this, starting from the end. So I'm going to start with how do I actually identify and check for unreasonability. So I do that with a set of rules, which and a constraint checker, which then outputs whether it's reasonable or not. So the first thing that I have to do is create that rule set. And the first thing I did was start with a set of baseline rules. And since I'm looking at the self-driving car domain, a reasonable place to start is with driving rules. And I used to think that this was a small technical detail, but Jacob Andreas actually pointed this was fairly interesting. I started by actually reading in a driver handbook, a PDF text. So I took in the PDF and read the individual words, and then I looked for key concepts. So I looked for key concepts that looked like something like a driving rule. For example, if you see a red light, then you should stop. So I searched specifically for those concepts, and then I generated rules from there. So I had a parser that took things I thought were rules and then generated that in the specific rule language that I used in my system. Now, there's a lot of pruning that has to occur. I didn't necessarily do that in code, so I manually went through and made sure that the generated rules were actually things that would be useful in my system. So what does that actually look like? You're not supposed to actually read what these rules look like, but I'll give a basic example. This is what a pedestrian rule looks like in AIR. That's a web rule language based on RDF. And what this says is that there are different things that you want to do if there's a pedestrian. For example, if you see a blinking red light, so the red light on a traffic signal isn't working, usually that means that you can proceed forward. Yet, if you see a pedestrian, there are different types of rules that you want to apply. And that's exactly what this rule is saying here. And when you combine that with the reasoner, then you can figure out which rules are triggered in these circumstances and use that to form a justification. Now, another thing that I did was the idea of how you can learn rules through explanation. So the idea here is that there are different contexts where different rules apply. For example, this is the parking structure at my undergraduate university, which is a very tall parking structure. And one day I was driving along in my car and I perceived someone flashing their high beams at me. Now, usually when someone flashes their high beams at me, that means that I should turn on my lights. But this baseline rule makes no sense in this context. Why would I want to turn on my lights in this parking structure? It was the middle of the day. Everyone could see me in my car just fine. And so what I realized is this was an exception, and actually I would want to make a new rule. Instead, in the context of a parking structure, could be some sort of warning signal. So this is to say, you know, either someone is crossing my path or I should be careful moving forward. And that's the methodology that I took to rule learning. So the big idea here is that if you look at the individual reasoning that comes out of my reasonableness monitor, so for example, in this case, if you looked at the explanation that said, oh, you know, you should turn on your lights because someone flashed their high beams at you, maybe you should think whether you should learn a new rule through that context. Maybe this is actually an exception. And so the way that this works is that you look at the explanation that you've got from the system, you introspect on it, and then add information about the environment. In my example, that's something like you're in a parking structure, it's very light outside, describing the world around you. You log that information, and then you use that to create a new rule in the circumstances. If this rule is similar to something you've seen before, then you don't make a new rule. And I'm happy to talk about the details of this offline. Now, that's sort of the idea of how the rules work in my system, but how do I actually represent different types of data? And actually, there's novel ways that we can use different types of representations that encode understanding. And this has been well studied for many years. I chose to look at conceptual dependency theory from Schenck. This is actually a fairly old representation, but what's nice about it is that these encode meaning. So in particular, I was interested in looking at the 11 primitives that account for actions. Again, I'm interested in actions because I'm looking at the self-driving car domain. And so those are these that are located, that are highlighted in yellow here, things like ingest and expel, grasp, move, and propel. Obviously, some of these are more applicable to self-driving than others, like moving and propel. And I also extended these to cover different vehicle primitives. So those are things like turning or yielding, things that aren't necessarily well represented by the primitives that Schenck created in 1975. And using these, I can represent different types of reasonable rules in the individual input to my system. And I'll talk through that in detail. So the way that this works is that I basically parse some sort of natural language into this representation. And this was done because we had an end-to-end demo of this system. But the way that this works is that if you take the same image that we looked at in the beginning, again, this is data from New Scenes, and this is labeled as a woman. And so the description of the scene is a woman crossing the street. I went along and built my own parser. So one of the other technical contributions of this work is that I did most of the backbone of the technical part. So I built this parser and then looked for the key concepts that were important in this description. In particular, I looked at the subject, the verb, the noun phrase, where they're moving towards, and I queried a common sense knowledge base to find the anchor points. That's the representation that I use that can represent a plethora of different situations. And so when this is actually represented in the conceptual primitive decomposition, it looks something like this. So crossing the street is characterized as a move. It's moving towards the street and the person is doing that action. Now, what's nice about this is this primitive actually has implicit reasonable rules. And those are really important for the reasoning that I'm doing in my system. So for example, the move primitive has two conditions. So if you're looking specifically at the actor that is moving towards a specific location, now this is a little bit different than what Schenk thought, but I'm inspired by his representation. I don't use it exactly. But here you have that if the actor has the property that it's adamant and the actor is located near the location, and we can look at that via the geometry of the image or other common sense knowledge, then we can deem the move to be reasonable. And I've represented this for all the different primitives that I use in my system. And the key point here is that a perceived frame or a snapshot of what you perceive in driving is reasonable if all the primitives, the primitive decomposition of that scene are reasonable. And that's a really key fact for my, for my judgments. Now, how did I actually implement this to do real world error detection? As I alluded to, I created an end-to-end prototype for machine perception where I represented Schenk conceptual dependency primitives. And so that was exactly what I did, where I parsed the natural language and then used the reasonableness rules to figure out whether it was reasonable or not. But then I also created a generalized framework using reusable web standards and extending the Schenk representations to cover a multitude of different primitives, the vehicle primitives that I talked about, like moving and yielding, and other things like the general location, like whether something can be located on top of the other. And so that was really important to be able to use this for a multitude of different domains. So how does this actually work in practice? I'll show this on real data. So this is actual data from New Scenes. And so what this looks like, again, this is classified as a human pedestrian adult. That's the most general judgment that they have here. And this is reasonable because it's direct data from New Scenes, which is a self-driving car data set. Then you can see the individual information that you get from this. So you get the general location, where it's located, its size, how many LiDAR hits, and things like that. Now, if you want to figure out whether this is reasonable or not, I go in and query common sense. But one of the biggest problems with querying common sense data is that it's very unorganized. If you take in all the common sense, then you're not going to get to a good judgment. In fact, if you look at the type of common sense that exists for just an adult, just the end term here, you find things like adult is capable of helping a child or dressing herself, driving a train, or explaining rules to a child. And that's not necessarily important for the types of judgments that I'm doing in my system. But things like the type of things an adult is, whether it's an animal or a person, and those have different properties, that is important. And so I created a way to prune out the common sense that's important for this application versus the common sense that's not. So in fact, what you get from this is the facts that an adult is a type of animal, an adult is bigger than a child, and only the things that are important for this justification. And so when you go through and put this into my reasonableness monitor, what you get is obviously this is reasonable, and you get again, you get a judgment. That's this first sentence here. So this perception is reasonable. And then the next few sentences say why it believes that. So that's the second part, the justification. It's because an adult is usually a large person. They're usually located walking on the street. It's the approximate dimension is correct. And so it knows that those are the pieces of information that support this reasonable judgment. Now, again, the focus of my research has largely been to detect errors that can cause failures. Now, one of the biggest problems is that you have to build your own error data set. And so one thing I did was I created an unreasonable image description data set with 100 descriptions with a various amount of words and different unique words that only occurred once, so it couldn't learn different trends. And also it had different prepositional phrases. Now, I also had to do this in the self-driving car domain. So one thing I did, which I'll talk about later in the presentation, is a real-time evaluation with Carla. That's a self-driving car simulator. But I also added my own errors on an existing data set. So again, I did that on the self-driving car data set, new scenes. I also looked at examining where people failed. So where existing algorithms failed on the validation sets of some of these leaderboards for different challenges. And I'm working on building different challenge problems and scenarios. Now, what's important about the part where I added my own errors is that's done randomly. So I'm not adding errors that I know my system can solve. So every time you run my error adding algorithm, it gets a different set of errors and it scrambles the labels in a different way and adds a different amount of noise. So I feel confident that that's actually adding errors that are out of the domain. So how does this actually work? So again, I take something like the label on this image from New Scenes, and instead I scramble it to something like a movable object traffic cone. Traffic cones and people are located near each other, so this could be a near miss sort of situation. Now, if I put this into my reasonableness monitor, it finds that it's unreasonable. And again, I get a judgment and a justification. So it says the perception is unreasonable, and now it gives the justification why. It says the movable object traffic cone is located in the center region. It's not reasonable size. It's too tall. And it looks for more information from common sense to support it and says it doesn't find any. And then it alerts the higher system that it should detect objects in the same region. Not that it should disregard it because the detection of something is important, but that the actual label is incorrect. Now, this vision system is just one part of a larger system. In fact, if we look at self-driving cars, they also have sensors that need to be monitored for their behavior as well. And so right now I'm going to talk a little bit about how I created a qualitative system that could describe sensor data. And the problem here is that sensor data is difficult to understand. It looks like just a set of points. It's largely a point cloud. What we would want is for it to come back and say the actual labeled output, which is that this scene is a pedestrian with a pet, a bicycle, a car making a U-turn, lane changes, and the pedestrian crossing a sidewalk. Further, you'd want to point to where it's actually identified. So you'd want to say, oh, I detected this pedestrian to the right, or I detected the bicycle to the left. And so that's exactly what I did with a qualitative sensor data interpreter. So it looks at sensor data, it performs edge detection, so it finds consecutive hits of LiDAR data, and then it does geometric analysis to track the object across several scenes. And then those qualitative descriptions that come out can be input into my reasonableness monitor for additional reasoning and justifications. So the big idea is that if you detect something like some sort of animal walking in front of your vehicle, it tells you the general size, shape that it's moving, and the general region where that's located in the frame of reference of the car. And so how did I actually do this? So I looked at the individual sensor data. And when I tried to apply geometric and qualitative analysis directly, it didn't work exactly. And that's because there's been a multitude of work to make sensor data more dense in the last few years. And so for the time being, I basically said I would take an intermediate step and process LiDAR to the way I process images. So instead, I take a deep neural network that looks at that sensor data and then produces a bounding box and location. Then I use that bounding box and location into my geometric and qualitative analysis tool, which outputs the qualitative description that I desire. So for example, the general size, how it's moving, how fast it's been moving, and where it's located in the frame of reference of the car. Now, I take these two pieces together. So I take reasonableness monitors, sensor interpretation, and I put them together into a full system design. And so the final contribution of my thesis work is a system-wide architecture that applies reasonableness monitoring and sensor interpretation to full system design. Now, to motivate this, I'm going to start with the deadly Uber self-driving car accident and talk why my architecture is so important. So again, if you will recall, the person came out from the shadows here, and what happened when they actually looked at the logs after the accident was that the vision system was unsure. And so what actually happened was that the vision system had labeled the person as an unknown object. It had labeled them as a bicycle, and a bunch of other things. And because the vision system was unsure, it basically deemed that it should be ignored. So it deemed that that object should be ignored just because it didn't know how to label it. And this is a bigger problem in self-driving. Again, the headline from this was that there was a serious safety lapse, but this is a much bigger problem of limited internal reasoning in complex systems. And that's largely what my architecture is trying to fix. This is one example of an accident. There was another accident where a Google self-driving car caused a crash for the first time. That's when the Google self-driving car thought the bus next to it was actually a cloud and it wasn't going to move, and that's something clearly unreasonable. And again, they have limited internal reasoning because you get this sort of herky-jerky, overly cautious behavior where it doesn't know whether it should stop for something like a plastic bag in the road versus a large moving object. And so what I did was I created a system architecture of reasonableness monitors along with an organizational architecture that can deal with these types of inconsistencies. So again, I took reasonableness monitoring to full system design. So I monitored the subsystems and combined that into a system architecture. At the high level, I have an explanation synthesizer that deals with inconsistencies between the underlying parts. And that produces an argument tree, which can then be queried for counterfactual. So you can look at different ways that that can be satisfied in different situations. Now, I call this architecture anomaly detection through explanations because the individual explanations from subsystems are what facilitates the better anomaly detection. And so the way that this reasoning works is largely in 3 steps. And we've seen the first 2 parts of it. So you start by generating qualitative symbolic descriptions for each committee or subsystem. And then you use those descriptions, you input them into a local reasonableness monitor for more reasoning, justifications, and evidence. And then you use an explanation synthesizer at the high level to reconcile the inconsistencies between monitoring outputs. So I'm going to go through these step by step, and I'm going to use the example of the Uber self-driving car accident to show the power of this architecture. So again, the vision system was very confused. It thought that the person was a vehicle, a bike, and an unknown object. Then if you interpret the LiDAR data with the analysis I showed in the last part, it finds that it's an object moving, it's about 5 feet tall, and the general location is in the top left quadrant. Then you can qualitatively describe the tactic system or the system state to say the vehicle is moving quickly, it's proceeding straight, and it has continued straight. Now, an important point is that this architecture doesn't just look at vision versus LiDAR, it's also looking at the system state. If your vehicle is traveling fast or slowly or given the environment it's in, it wants to make different decisions. So again, I take those qualitative descriptions and I input them into a reasonableness monitor for more reasoning. So for the vision system, we put that into a reasonableness monitor and it finds it's unreasonable. It finds that the vision perception is unreasonable. There's no common sense data supporting the similarity between a vehicle, a bike, and an unknown object, except that they can be located in the same location. And then it indicates that the component's output should be discounted in this case. Now, if we look at the LiDAR system, it finds that it's reasonable because an object moving of this size is a large moving object that should be avoided. So it gets more information about the object and finds that it's something that could be threatening. And I'll return to that fact moving forward. Now, if we look at the vehicle state, the moving quickly, proceeding straight, and has continued straight, that finds that it's reasonable, and it finds that it's reasonable given that the vehicle has been moving quickly and proceeding straight for the last 10-second history. So it does look at some of the previous data here. Now, we put those explanations into the synthesizer, and what we get is the explanation I showed at the very beginning of the talk. So it recommends that the best option, this is its judgment, is to slow down. And that's because the vehicle is traveling too fast to suddenly stop. The vision system is inconsistent, but the LiDAR system has provided a reasonable and strong claim to avoid the object moving across the street. Now, this is also stored as symbolic reasons that can be used for the machine. So this isn't all done in natural text. I have a translator that takes these symbolic reasons and turns that into the natural text to be shown for demonstration purposes. And you can see where it actually gets this information. So this is highlighted in yellow and blue and red. And you can see exactly where that comes out in the synthesizer's explanation. Now, this may seem like a little bit of magic, so I'd like to dig into what exactly the synthesizer does. Well, the synthesizer has to know what the priorities are that you want to do in the specific application. So again, the synthesizer is meant to deal with inconsistencies by producing an argument tree, and it needs to figure out what the priorities are of that system. So you do need to give it a priority hierarchy. Now, for my application, I define that in 4 steps, which I'll go over in just a second. But taking the synthesizer along with the priority hierarchy, you get a set of abstract goals. And that's exactly what have to be satisfied for different properties, to have different properties in your system. So the priority hierarchy that I look for in this specific application is passenger safety, and then perceived safety, comfort, and then efficiency, which can be defined for a bunch of different things. For this example, since safety was obviously not met, I'm going to focus on what the safety constraints look like. And this is abstractly defined as a passenger is being safe if it proceeds at the same speed and direction and it avoids threatening objects. So basically, you want to have a smooth ride, but you also don't want to run into things that can harm the vehicle. And so how do I actually represent that so that my system can reason about it automatically? And so that's represented as this sort of first order logic. So for all states, so for a state T that succeeds a state S, if you've been moving at the same qualitative velocity at both states, then it's proceeding at the same speed and direction, and there are no objects in that scene that have been classified as threats. Then you can say that the passenger has the property safe. Obviously, there are many other conditions that you may be interested in, but this is the most basic representation for this problem. If you're interested in the other sorts of representations and ideas of safety, we can talk about that after the talk. So again, you have to define what a threat actually means in this circumstance. And again, I can define that in logic. So a threat is defined as a large moving object that is located near the vehicle. And that's defined like this. And so that is how you define a threat. And that's the underlying backbone of how this reasoning works. And so again, this is then represented in an abstract goal tree that can be queried in different circumstances. And we see that the safe transition is defined here by the stuff that's underlined in green here. And then the not threatening objects is defined here. All of the objects in the scene are not defined as a threat. Now, this is a very abstract goal tree. I'm going to show a little bit of what's done in code. Again, this is just to show the technical part of it. So again, this is done with a list of rules. So that first order logic is represented as a bunch of rules. So this is the one for the smooth ride here, and this is the one for not having threats. Then I backwards change those rules to be able to create an and or tree to make sure that those properties are satisfied. I do this for each one of the priorities. Again, we're only looking at the first priority in this presentation. And so that looks something like this, where the passenger is safe as long as it's a smooth ride and it's not a threat at either one of the timestamps. Now, we'll be using the abstract goal tree just to illustrate examples. So this abstract goal tree is then used along with the input explanations. And what the synthesizer finds is that this property from the LiDAR system violates the not threatening object rule. So what it finds, it doesn't find anything with the vision system. It just finds that the LiDAR system is actually proving a point that should be recognized in this situation. So again, it's looking at multiple modalities in different environments. And so that's exactly what leads to this sort of explanation at the end. Now, how did I evaluate the system? So I went through a long example, but I evaluated this in simulation. So with one of the Europe students, Vishnu, we went through and simulated this in Carla. And so you'll see here, there's a person who's crossing the street here in red. And you'll see that the system actually detects it. It finds that the vision is unreliable and the LiDAR detected a large moving object. And now I also evaluated this after the fact and added the actual information. So unfortunately in Carla, they didn't have the option to put a bicycle with a person next to it, but I added that information to do an after the fact analysis. And so again, that's one part of the evaluation that I've done, which is on real world inspired scenarios. And there are a number of other pre-crash scenarios that can be simulated and done with the same type of reasoning. But now I also wanted to make sure that this doesn't just detect inconsistencies, but can also reconcile them. And so that was the first part. So I looked at these logs of accidents after the fact and made sure that they detected the failure and they pinpointed the root cause of that failure. Then I also did the insertion of errors. So this is what I had alluded to earlier. I created a random algorithm that would look at a data set and randomly scramble 50% of that data for multiple modalities. So it looked at both the LiDAR data and the vision data, and with a ratio of half-half, it figured out whether it should insert an error or not. And I ran this several times. And so what I got was that when I looked at this against my synthesizer, if you use no synthesizer, it didn't do very well. So it got many false positives and false negatives, versus when you said, okay, I'm just going to trust a single part versus another one, it did a little bit better. And if you actually prioritize safety, it finds these errors much better. Now, there are some false positives and some false negatives, and the reason for that is because the errors that I'm adding are very small. So what I alluded to again was that this is a protocol that I wrote that would just add a little bit of noise to the LiDAR or scramble one of the labels very close to what it should be. So obviously it's going to mess up a little bit of the time because these are very close. A lot of these are not clear errors. Now, another thing that I wanted to do was to examine the errors on the validation sets of some of the new scenes leaderboard. Unfortunately, most of these algorithms are either proprietary or they're only looking at a single modality, but this is something that could be explored in future work. And so now I've talked about what I've done in my thesis, but to conclude the technical portion of this talk, I'd like to discuss where I think we should go. And I think we can go towards articulate systems by design. I started this talk by talking about the problem that complex mechanisms are imperfect. And what I've described in this talk is a way to use explanations to be able to deal with that type of problem. And in fact, if you look at the explanation literature, I had the opportunity to work with a multitude of collaborators on a review of the explanation literature. You'll find that no one is looking at explanations that are dynamic, so explanations in uncertain situations that can actually explain failures, and how you can use explanations for the machine. So how you can create architectures that explain themselves and use that to make better decisions moving forward. And this is all leading towards my vision of having machines that are articulate by design. And so these are machines that can communicate coherently and clearly. And this is not just for communication with a human, this is also for communication with another system. What I've shown through this talk is the way that you can take the outputs of some sort of opaque learning system and feed that into my symbolic system to do a last pass check or sanity check on some of these outputs that just don't make sense in that context. But what if instead you actually used explanations as a common language for these two systems to actually learn from each other? That's important for redundancy. Opaque learning systems and machine learning solve problems in very different ways than symbolic systems and even humans. Maybe they can learn insights from each other moving forward. And that's also important to actually create the hybrid processes and systems that people argue we need for true artificial intelligence systems. Largely, these are described as type 1 and type 2 systems, but what if you created a common language where a symbolic system and a learning system could actually work on tasks together? I think that's a really exciting area that we need to work on. If we look at the other aspect of how you communicate with humans, then you can think about explanations as a common debugging language. This is for debugging where humans can improve complex systems. This is largely the task that we do as software programmers. But what if the explanations were actually twofold? So the complex system could actually come back and teach you something and actually explain where it failed. I think that this would be a remarkable next step to create better software systems that are robust and also can explain themselves in these sorts of failures. And this has impact across the board, not just in the self-driving car domains that I've largely looked at for my thesis, but also for society, so that systems can articulately communicate with humans on different types of shared tasks. This is also for liability. I described that one of the use cases of explanations is for a human, possibly a human auditor. And imagine if you had a system that could not only explain itself, but it could also testify. It could answer questions and provide insights, especially in the case of failure or accidents. And this is all leading towards better system robustness. So using my dynamic self-explaining explanation system, you can dynamically detect failure and intrusion with more precise mitigation. And so the contributions of my thesis, I started by talking about a difficult problem, which is that complex systems are prone to complex failures. And one way to fix that is with better communication and better sanity checks. And that's using explanations as both a language for the machine to do better and also to prove that to a human. I described a reasonableness monitor that can justify and explain different types of opaque outputs. And I also described a way that you can help sensors explain themselves using a qualitative representation and interpreter. This is all leading towards a system-wide architecture that uses these sensor interpreters and reasonableness monitors and applies it to full system design, an architecture that's able to reason about unreliable parts, and this relies on the fact that explanations facilitate a common debugging language. Now, this concludes the technical part of my thesis contributions, but I want to go forth and acknowledge some people that this work could not have been done without. As Patrick Winston said, you can do it, only you can do it, and you can't do it alone. First, I really want to go and thank my committee, Jerry Sussman, Leilani Kagal, Jacob Andreas, Julie Shaw, and Howard Schroeb. It's hard to know what to say about Jerry, but when I was thinking about it, I really just want to say that he really personifies what it means to be an educator. I've learned from him. My first year, I think we sat together for a year and we side-by-side coded, which is something that not many students can say they did. But also I've had the opportunity to teach with Jerry, and it's just been a remarkable experience where I've learned about software, I've learned about robustness, I've also learned about physics. I think the other nice thing is that Jerry's students are friends for life, and I'm excited to move forward in that journey. And I'm very thankful for the opportunity we've had to work together. I also want to thank Leilani Kagal, who's largely been the co-supervisor of this work. She's really given me a lot of help with implementation details and thinking about different semantic web technologies that are applicable. And she was especially helpful when Jerry was on sabbatical and really pushed the work forward in what I think is a really strong technical direction. So I'm very thankful to have you on my team. I was really excited to invite Jacob Andreas to be on my committee, specifically to sort of bridge the gap between the symbolic approaches that I work on and the new age machine learning aspects that he works on. I'm a big fan of his work, and he's given some really great feedback for next steps. And he's also pointed to some things that I thought were small technical details that he said are actually very interesting details that I'll be elaborating in my thesis. Julie Shaw is just, a wonderful mentor and fan of this work, and I really admire a lot of the work she's done in interpretability that's inspired a lot of this work. And I think that her work on robotics and her use cases of looking at these applications has really strengthened this work. So I've been very happy to have her on this team as well. And last but not least, it's been an absolute joy to have Howie on my committee. Jerry was like, you have to put Howie on the committee. And he's really given remarkable feedback, both through the COG AI community, but also, small technical details that I should talk about and think through in my thesis. So I'm very thankful to have this wonderful team supporting my thesis work. I also want to acknowledge the funding support that I received for this. So this has been funded by the Toyota Research Institute. I want to acknowledge Paul Drews and Luke Fletcher, who have been our liaisons through this process. Luke's been with us since the beginning, and he's really given remarkable feedback throughout the course of this thesis work. I also want to acknowledge the Sloan Foundation. I've been a USM Sloan Fellow since the beginning of my PhD, and that's given me a really great community and people to talk to and mentor throughout the year. And speaking of community, I want to briefly acknowledge the general MIT academic communities I've been a part of. That includes the Internet Policy Research Initiative, where I've had the opportunity to go to China, to DC to talk about privacy legislation, and also a really great group of friends. I've also been lucky to be a member of the Genesis group since the beginning of my PhD. Randy is now the lead, and I've gotten remarkable feedback from Randy and the other members of the Genesis group. And we've also had a lot of fun and gone to conferences together. And I want to briefly acknowledge the greater EECS and CSAIL committee. I've been a member of the GSA, the Graduate Student Association, for many years. And in particular, I've gotten the opportunity to work with Cecilia Testert, who's also a member of IPRI. And she's just been a really great support and friend in many different endeavors. As Patrick would say, it's important to talk about your fellow travelers, and those are collaborators that I've worked with. Firstly, the long list of Europe students I've had the great pleasure of mentoring throughout the years, and now they're off doing really wonderful things. It's been really fun to work with these students, and also the master's students I've had a chance to look after, but also the different collaborators I've had here at MIT and the different co-authors that I've worked with throughout the years. And there are many more from Park and IMRIA, Stanford, and UCSD. In particular, I want to talk just a little bit about the people from my previous academic pursuits. As Jerry alluded to, I spent 2 years at Park, which was a really wonderful 2 years. I was very influenced by the work of Johan and Danny Barbaro and Matt Plank and others. And some of those people are here in the Boston area, and they're in the same academic communities that I'm in now. So it's been really great that I had this time at Park to meet a lot of great people. I also was at Stanford for 2 years doing my master's in computational math, where I met Carrie Ann Bergen and Chin Yang, who have been long-term friends, and they've just supported me through many different things. Here we are just a few months ago in Boston, and they're early career scientists who I really look up to, both as academic people I would like to be more like, and also as wonderful friends. I briefly want to mention a few people from UCSD. So Mark and Stefan have been huge supports. The general CSE tutor community, these are people who sit in the labs and help you debug programs, and I was lucky to do that throughout my undergrad. And also the Mathematical Beauty of Rome family, we call ourselves. It was a really great opportunity for me to go overseas, and I met some really lovely people. Speaking of family, I have to acknowledge the great one that I have, my parents, Brian and Patty, and my brother, Corey, who have been extremely patient with me, even when I can't make the family photo for Thanksgiving. I'm there on the iPad. And since it's been difficult for me to get to the West Coast during this time, they've even come to visit me in Boston. My greater family on the West Coast, my extended family, have been remarkable during this journey, and I can't acknowledge their support enough. And I also want to briefly acknowledge those who can't be with us today. The strength and support and perseverance of my grandparents has really made this work as strong as it is today. And now my family away from home has largely been the social, living, and athletic communities I've been a part of. So as Jerry said, I was a GRA at Burton Connor for 4 years. I really enjoyed living in Burton 4, and I was very sad when I had to leave before COVID. I had a wonderful group of house staff members. Here's the group of GRAs and those who couldn't make it into this photo but are still very important. I've also been involved in a number of club sports. So I've been involved with the MIT Rowing Club. I even got to row in the Head of the Charles, which was a unique experience. And sometimes I dabble in other water sports as well. But the one thing I want to talk about is that I never knew that I would make such wonderful friends through these communities, and they even make me leave the lab when I don't want to. I want to take a brief moment to acknowledge my roommates who took me in, especially during this difficult time of COVID. That's Ray, Veronica, and Raz, who's also my partner. It's hard to know what to say about Raz, but you really personify what it means to be a partner. You're extremely supportive, and I think that I'm very lucky to have someone by my side who not only deals with my worrisome attitude, but can also give very good technical advice when I need it. And finally, the friends who I haven't mentioned before, the Chicks of Course 6, or the group of women from my cohort, have been a great support system, and we still meet for breakfast regularly, and I look up to them in many more ways than I can say. And I want to acknowledge, I think I got everybody, a group of friends who came and visited me in Boston during this 5-year period. I know that it's been a long time since I've been at home, and I feel very blessed that I have a wonderful group of friends who I can call at any time of day. It's especially useful when I have coding problems at midnight, and I can call those people in California when it's just 9 o'clock. And last but not least, there is one person who can't be with us today, and that's Patrick Winston, who we lost earlier this year. Or earlier last year. It's hard to know what to say about Patrick. He really was a huge mentor to me. He invited me to join the Genesis group when I started my PhD. And he really took care of me when Jerry was on sabbatical. I think very fondly about our weekly meetings during that time. He taught me the power of a good demo, how to communicate. And again, he gave me this wonderful community with Genesis where he showed that everyone can help towards a greater goal. And he fostered the spirit of collaboration and communication wherever he went. And, you know, I hope that those themes are present in the technical contribution of my thesis, because Patrick didn't only teach me how to communicate, but he also taught me how to use those skills in my technical work. And if there's anything that I can get from Patrick, is that he said the best thing you should do at the end of a talk is to salute the audience and reiterate the contributions. And so that is exactly what I will do. I'm extremely happy to see that so many people have been interested in this work. And I hope that this has illuminated you to think about a new way to think about explanations. Explanations are not just for a user, but they're also for the machine. I started this talk by talking about the fact that complex systems need better communication and sanity checks. And I went through a couple of those sanity check methods, reasonableness monitors for opaque subsystems and qualitative representations of sensor data. I tied that together into a full system architecture that can reason about its underlying parts, and that all relies on the novel contribution of explanations as a common language. For those of you who are interested, you can read more about this in some of my work, and I hope that you will take this and move this idea of explanations moving forward. Thank you.